Good morning, everybody. I hope you guys are doing well today and had a great Thanksgiving. Well, at least you earned some money doing that. It's not a total wash then. Awesome. All right, so when I left you off, we were talking about graphs of trig functions and we focused on sine and cosine to begin with. Today, we're going to look at the other four trig functions. Before we do that, though, I just want to throw out an end of the semester announcement real quick. So I know it seems like it's far away, but technically it's only 6 weeks. So 6 weeks from now puts us at January 14th, I want to say. And that is when all work besides the final exam has to be turned in by. Okay, so just kind of keep that in the back of your mind there. I believe January 14th is a Sunday. And then January 15th kicks off final exam week. So the 15th through the 18th will be final exams, and then Friday the 19th you'll have off. The 22nd of January will start semester 2. So we'll just kind of pick up wherever we left off at the end of semester 1 then. All right, so again, January 14th is that deadline to get all your work in. Now, hopefully, if you're staying on pace with the calendar, that's not going to be an issue whatsoever. But it's also hard to believe that it's only 6 weeks away. So we've got about maybe 4 weeks here only until winter break. And then after winter break, only 2 weeks until final exams. So it's going to come up fast. All right, so before we start with the lesson today, 4.05, were there any questions with 4.04 with the sine and cosine graphs? Yes, phase shift comes from adding and subtracting inside your parentheses and adding and subtracting outside of the parentheses. So when we talk about phase shift, and we'll continue with this topic a little bit more today with the other trig graphs as well. But if you're working, let's say, oopsie, sorry about that, inside here, I'm just making something up. You do have a couple of phase shifts. So obviously the +7 at the end is telling you whether there is a vertical shift happening. Are you shifting up or are you shifting down? And that depends on the sign that's there with that constant at the end. So with the +7, that means you are shifting up 7. Right? And that's kind of we kind of figured that because with our normal polynomials, that's the same effect that the shifting up or down had. It was always the constant kind of on the outside of any type of parentheses. All right, if it was inside parentheses, we may have to do a little bit of work to solving for x in here, and that's going to help you decide if you're shifting left or right. Now, I always told you to do opposites, right? Well, in this case, and I think there was one that had a pi in it, I believe, that may have threw a couple people off because it looked like it was just a pi over 2, I think, right out here. And I think that threw a couple people for a loop because there was another value, I think it was a 2x minus pi over 2 or something like that. So if I may have the sign wrong, I apologize. Something like this inside there. And a lot of people were like, oh, we moved that to the right, pi over 2. Well, technically, yeah, but there's a little bit more to it. The 2 in front of that also plays into the shifting of it. So I would take that whole lot or that whole set inside the parentheses there, and I would solve for x with that. So I'd end up having to add the pi over 2 first, and then dividing by 2, which is the same thing as multiplying by 1/2, right? So if I multiply by 1/2 here, or divide by 2, you'll get rid of that and you'll just have x equals. And that's really shifting it a pi over 4 to the right then, because when I solve for x there, it ended up being positive. So that means you shifted it to the right. So you do have to take into consideration if there's a value in front of the x as well for that shift left or right inside the parentheses there. I think that's what a lot of people ended up missing. Yeah. It also will help with, well, technically it's not a horizontal stretch because the 3 is not necessarily being affected inside here. It's just kind of the x. But you could look at that as a horizontal, well, this would be a horizontal shrink by 1/2, but it also affects the shift as well. So that 2 kind of has a dual purpose in the equation. Okay. And again, like I said, we'll kind of practice with this a little bit still today as we move through these other trig functions. So hopefully that clears up things just a little bit, because I did see that phase shift on that one question in 4.04 with that pi over 2 versus pi over 4 being a problem on many a student's assignment. So it wasn't just the one person, many people had that same error. So thank you for bringing that up. Were there any other questions with the sine and cosine graphs? All right, if not, let's go ahead and move forward. The first trig function we're going to look at, obviously, is tangent, because that's the third kind of trig function that we have with the SOHCAHTOA, right? So sine, cosine, tangent's always that third piece. Now tangent's a little bit different though, because tangent is made up of the sine and cosine functions, right? It's actually a fraction of them. So tangent can be represented by sine over cosine. This is not a continuous wave like sine and cosine were. Because you now have a fraction, you're going to have some problematic areas because you know the denominator of a fraction cannot equal 0. So wherever cosine of x does equal 0, you're going to have what we call a vertical asymptote appearing at that spot. And that's where all of the vertical asymptotes are actually created with these other trig functions, right? You have reciprocals of your trig. So obviously you have fractions being created, and anytime there's a fraction, when that denominator equals 0, you're going to have a vertical asymptote appear in your graph. So the remaining pieces or the remaining trig functions are all going to have vertical asymptotes somewhere because fractions can be created from those functions. All right, so some main features here of the tangent function. Obviously, we do have the asymptotes. The asymptotes are appearing at pi over 2 for all odd integers k. So basically, you're just taking multiples of pi over 2. And that is where the vertical asymptotes are appearing, both positive and negative, right? So you can have negative values as well for k, not just positive. The range is going to be all real numbers because remember, range is referring to your y values. So the y, there's no restriction on your y values here in the tangent function. It is symmetric to the origin, and we don't want to confuse this with where the vertical asymptotes are going to be located. The graph itself is what we call odd because of the symmetry that it has. So when we look at the very end, I have kind of a summary of the 6 trig functions and like their periods, their asymptotes, their x-intercepts, stuff like that. So when I go to sum all of that up, sometimes we'll confuse the asymptotes with the function itself, and we don't want to do that. So when we say there's odd multiples or it's even multiples of something, it's not coming from the symmetry of the graph. All right, so we don't want to confuse those two pieces. It'll make sense what I'm talking about when we actually get to the problems a little bit later on. So the main thing to take away here is because tangent can be written as sine over cosine, you have vertical asymptotes at the sine, or where cosine is 0, and you have x-intercepts where sine of x equals 0. Right? So the numerator are always the x-intercepts of the graph, and the denominator are going to give you your vertical asymptotes. All right, let's go ahead and take a look at an example that deals with our tangent function. It says, describe the graph of the function y equals negative tangent 2x in terms of a basic trig function. Locate the vertical asymptotes and graph 4 periods of the function. So when it says describe the graph, it's asking for the transformations that are occurring. So are there any shifts, left, right, up, down? Are there any stretches, shrinks? Are there any reflections? That's what it means when it says to describe the graph. So let's go ahead and look at those transformations that are occurring. What's occurring in this? A reflection across the x-axis is the first thing that Tommy throws out. I like it. That's the negative sign. So the negative sign in tangent is that reflection across the x-axis. Careful, it's not a vertical stretch. It is a horizontal shrink, yes. Now notice that, I'm going to finish writing what Isaias had there. Notice that it's inside the tangent here. If it was a vertical, it would have been outside by the negative sign. So the outside part by the negative sign is your vertical stretch or shrink. If it's inside attached to the x, that's your horizontal stretch or shrink. When you're talking about horizontal, you always want to think reciprocal. So because that's 2, to find what you're actually stretching or shrinking it by, you've got to take the reciprocal of that. So that's where Isaias got the 1/2 from. Right? And 1/2 is representing a shrink. So that is going to be a horizontal shrink by a factor of 1/2. And I'm going to highlight that so it's reflected, or just not reflected, but color-coded in the equation there. All right, now it does say to locate the vertical asymptotes and graph 4 periods of the function. We should be able to find the vertical asymptotes without having to actually look at the graph. So when we go back to the description of our tangent function, it says that our vertical asymptotes are appearing at odd integers of k, or basically odd multiples is what we like to call it there, not necessarily odd integers. We say odd multiples of k. Now, it is pi over 2, so I'm going to go ahead and write that to begin with. However, horizontal shrinking and stretching is going to affect your asymptotes. So anytime you have a horizontal stretch or shrink, it's going to affect your asymptotes. So originally we had pi over 2, and let me write this. So originally it's going to be odd multiples of pi over 2. However, because you have that horizontal shrink, that's affecting the asymptotes. So you're going to multiply that pi over 2 by the horizontal shrink that's occurring. So now you're going to say that you have odd multiples of pi over 4. Yep. So your vertical asymptotes are actually occurring at odd multiples of pi over 4 because that horizontal shrink affected where those were happening. The vertical stretching will not affect that because if you think about it, vertical is stretching it kind of up or down. That's affecting your y coordinates more, not the x's. But when you're talking about horizontal, that's left to right. So you're kind of stretching it or compressing it, like shrinking it, pushing it together more. That's affecting those vertical asymptotes because it's changing your x values of the graph, right? So hopefully that makes sense that only the horizontal stretch or shrinking is going to affect your asymptotes. Now to graph it, I would just use a graphing calculator. I'm not expecting you guys to actually do these by hand. So GeoGebra, Desmos, actual graphing calculator, I know you guys are really good with those. Let's go ahead and instead of using the one in the room here, let's just type that into our actual calculators. And again, we may have to check our mode if the graph doesn't come out like how we want it to. So I'm going to have to change my window because obviously I tinkered with it. If you ever need to get back to the 10 by 10 viewing window, you have to go to it's zoom button right in the middle here, the zoom button, and then number 6 is the standard coordinate plane. So if you just hit zoom and then number 6, it's going to give you back to that window. Okay, now my graph doesn't look the greatest there, so that means I may have to switch my modes. Yep, I was in degree mode, and that could have been from a different class. So I originally was in degree. I'm going to change that back to radian and try graphing again. That looks a lot better. That looks like the graph that we had on the previous slide. So if you don't get that traditional graph that you're originally searching for there, change the mode in your calculator. It does kind of look like beach waves. Sideways, I guess if I were to flip it, it looks more like it. But yeah, coming into shore, if you're standing off on a pier or something, yeah. All right, so then there you can actually see your odd multiples of pi over 4 for the vertical asymptotes that separate those waves. The only reason you like your tangent graph, huh? All right, any questions with that? Especially the vertical asymptote piece. I think for some reason, I think the vertical asymptote piece is always the part that kind of students struggle with. Okay, we've got 3 more functions to talk about here today. They're going to go pretty quickly though because now that we've seen the tangent function and how we can find those vertical asymptotes based off of the fraction that's created, the rest are just going to kind of follow suit. So for cotangent, that's the reciprocal of tangent, right? So instead of having sine over cosine, now you have cosine over sine. So where your x-intercepts occur and where your vertical asymptotes occur are flips, essentially. Your vertical asymptotes are occurring where sine of x is going to equal 0, right? Because that's the denominator of your fraction. And your x-intercepts are occurring where cosine of x equals 0, because that's the numerator of your fraction. The other thing that I want to point out for tangent and cotangent, the period of a graph is only pi over b. So I want to just mention that. Usually b is 1 because b is that number in front of the x. However, because it does change a little bit, we can remember that pi over b. So if you're ever asked to find the period of tangent or cotangent, we use that pi over b formula. So I forgot to mention that on the previous slide, but that's what we would use with tangent. That's different from sine, cosine, cosecant, and secant, because in the other four, it's 2 pi for your period. But in tangent and cotangent, it's only pi, or technically pi over b, whatever b may be. Okay, let's go ahead and take a look. You'll notice that I went through these, I'm going to go through these other ones pretty quickly. Let's describe the graph, and then we'll locate our asymptotes. All right, so let's figure out what transformations are actually going. It is the absolute value of b. Yes, Isaiah, thank you. It is going to be the absolute value of b because it's not going to make sense to have a negative period, right? It's only going to be a positive amount there. Yeah, exactly. Sorry about that. All right, let's look for our transformations. When you see a transformation, any transformation, go ahead and throw it out in the chat box. Yeah, there's a vertical stretch this time. So I'm going to color code this while you guys are still throwing out the transformations. Up 1 unit. Good. That's coming from the +1 at the end. And I think I saw Tommy had it. Vertical stretch. Good. Notice that when she took her vertical stretch to find the factor, she took the reciprocal of what was inside there. So traditionally we just got a 1/2, right? But the reciprocal of 1/2, oh, thank you. The reciprocal of 1/2 is going to be that 2. Come on. It's not letting me type. Oh, I know why, because I'm in the highlighting portion. Okay. I said horizontal, but I think I wrote vertical, so I apologize. There we go. That's better. Thanks, Isaiah. All right, any questions with the transformations before we move on to the asymptote piece? First of all, before we look at the asymptotes, let's find the period of our graph. So period can be found by doing pi over absolute value of b. I like to do just b because common sense will tell me that it's got to be a positive value there. But mathematically, we should probably leave the absolute value sign. What is b in this case? What is the value for b? Yeah, it's the 1/2. It's also how it helps you find the horizontal factor there. So it is the 1/2. Because we can't divide fractions there, it does turn into a multiplication problem. You had a pi over 1 times 2 over 1, right? So to change the division into multiplication, you take the reciprocal of that second fraction, or in the denominator there. So the period here is actually going to be 2 pi. All right, let's find those vertical asymptotes. We still have the pi over 2. So this time we don't have the odd multiples, it's just multiples, I believe. So usually it's just multiples of pi over 2. However, you had a horizontal stretch occurring. How is that horizontal stretch going to affect your asymptotes? You have to multiply by, not 1/2, you have to multiply by 2. Notice how the horizontal stretch was a factor of 2. So technically you want to multiply by the 2, not b, but the actual stretch that's occurring. So that is by 2, which means you're going to have your vertical asymptotes being at multiples of pi. Because notice when you multiply by the 2, those cancel out and you're just left with that pi. Okay, any questions with that? It takes a while to kind of get in the hang of those vertical asymptotes and how the horizontal stretching and shrinking affects them. So, but once we catch on to it, then they're really not that bad. Okay, so we got, what, 2 done? We've got 2 more to look at, halfway there. So the next one we're going to look at is the secant function. Remember, secant is the reciprocal of cosine. So we can traditionally write that as 1 over cosine. So you're going to have vertical asymptotes appearing where cosine of x equals 0. That means the vertical asymptotes are going to be the same as your tangent was, right? Because tangent also had cosine of x in the denominator. So your vertical asymptotes are going to match up nicely to whatever the tangent function had. The graph does look a little bit different though because you have 1 in your numerator, so you do not have any x-intercepts here unless a certain transformation of some sort may be occurring. But usually that would only happen if you're moving the graph up or down enough to have one of these pieces actually crossing over. But the normal parent function of that, you will not have any x-intercepts because there's no variable in your numerator. You will have maximum and minimums of the graph though now. So notice that that's occurring at the high and low point of that cosine wave. Okay, so I'll let you kind of take in that graph a little bit. And let's go ahead and take a look at a question with this. Now, because we're looking at the reciprocal of cosine, the period has now gone back to 2 pi over the absolute value of b, right? So tangent and cotangent were the only graphs that had that period of pi over b. Everything else is 2 pi over b. All right, this one's a little bit different. It says find the value of x between pi and 3 pi over 2. That's going to solve the equation secant of x equals -2. So they switched it up a little bit for us. They're not necessarily asking us for the transformations that are occurring of our graph. They're asking us to solve instead. We're going to really focus on solving our trig equations in upcoming lessons. This is kind of just an intro and starter one. This is very basic. We are going to get more advanced with solving trig equations as we move forward. This can be done with your unit circle though. So first of all, we have to decide what quadrant are we actually looking for an answer in. So it says find the value of x between pi and 3 pi over 2. What quadrant of my unit circle is that referring to? So pi and 3 pi over 2. Yep, that's your quadrant 3. So if I were to put my little quadrant up here, pi to 3 pi over 2 is somewhere in here. All right, it has secant equaling -2. They are numbered, yep. This would be quadrant 1, 2, 3, and 4. Good. All right, secant is not one of our values on the unit circle, but we said cosine was. So I'm really looking for cosine of x equals what? So if I'm going to change secant to cosine, what am I going to do with this -2 value? You're going to take the reciprocal of it, right? Because that's what I did with secant. Secant was originally 1 over cosine of x. So if I'm writing just cosine of x, I took the reciprocal there. I've got to take the reciprocal of the other side as well. So I'm going to make that a -1/2. All right, using your unit circle, remember that unit circle is going to be our best friend. We didn't think so when we're looking at the graph so much, but we still rely on it. Where is cosine going to equal -1/2 in quadrant 3 of your unit circle? Remember, cosine is referring to the x values of your ordered pairs there. So Isaias has 4 pi over 3 or 240 degrees. Anybody want to second that answer? Or did somebody get a different value? Tommy's going to second that, and I will third it. So I got that same location, so same answer. So x would be 4 pi over 3. They're probably looking for that radian answer versus the degree one, only because they gave us pi and 3 pi over 2 instead of the degree values there. So I would traditionally answer with the 4 pi over 3, but I like how Isaias included the 240 with it. All right, any questions with that one? And like I said, this was just the very beginning of solving. We're not going to really look at solving too much in this lesson, but as we move forward, it's going to be one of our main goals and one of our main focuses coming up. All right, last one is the cosecant, and that's the reciprocal of sine, right? 1 over sine. So obviously your vertical asymptotes are occurring where sine of x equals 0. You will not have x-intercepts again here because cosecant does have 1 in the numerator, right? And no variable is present there, so there shouldn't necessarily be any x-intercepts unless you have phase shifting occurring. If you have a phase shift up or down where it's dramatic enough, then you're going to have some of these blue graphs crossing over the x-axis. But that's the only way that you're going to end up with x-intercepts there. All right, again, the period for a cosecant, if you need to find that, is 2 pi over b. All right, let's move forward. And, here's the nice summary of it all. So I think the biggest thing to keep in mind is when we're looking at the asymptotes right here, how do I know when it's odd multiples or just multiples? So I told you don't get confused with when you should put odd multiples of something or just multiples based off of the even or odd function itself. So don't look at this to decide if your asymptote should should have even or odds. What you're going to look at is if there's a plus n pi at the end. If you have a plus n pi at the end, that's indicating odd multiples. Right? So only tangent and secant will have odd multiples. Everything else will just be multiples of the pi there. Okay, let's go ahead and see if we can describe the graph of each of these trig functions here. So first of all, we'll describe the graph, then we'll locate the asymptotes. So what transformation is occurring with this first one? Yeah, and you're going to notice that a lot of the transformations are regarding horizontal stretches or shrinks with these. And the reason for that is because the horizontal stretching and shrinking is going to affect your asymptotes. Nothing else affects the asymptotes except the horizontal stretching and shrinking. So they really like to throw those in with these functions. All right, so you do have a horizontal shrink by a factor of 1/2. I like how Tommy took the reciprocal of the 2 that's next or in front of the x there. You do want to take the reciprocal of that to decide whether it's a stretch or shrink. All right, let's find those vertical asymptotes. Vertical asymptotes, this is tangent, so you have odd multiples of pi over 2 to begin with. However, what are we going to do to figure out where those asymptotes are actually occurring? You have to multiply it by that stretch or shrink in the horizontal factor there. Yep, so technically that's going to be a pi over 4. So your vertical asymptotes are occurring at odd multiples of pi over 4. All right, we're really starting to catch on with those vertical asymptotes, so that's good to see. All right, how about the next one, secant? Let's start with the transformations that are happening there first. What transformations are happening with secant of 3x? Yep, good. Now, secant, if I look up at my chart, the vertical asymptotes there were also odd multiples of pi over 2. However, it's not going to be pi over 2 anymore. Where are my asymptotes occurring? So vertical asymptotes are occurring odd multiples of, yep, so when I multiply those together, pi over 2 times 1/3 gives us what? Pi over 6. Good, so hopefully we're going to start to get this in our head, that we're going to multiply by that horizontal factor before I write my final answer for the asymptotes. Good, so odd multiples of pi over 6. And the pi over 6 came from pi over 2, which was the original asymptote there, and then we had to multiply by the horizontal shrink. So if you're wondering where the pi over 6 came from, that's how we got it. All right, any questions with those? All right, we are flying through. Oopsie daisy. All right, let's look at this. We've got a couple things happening in this cotangent one. Let's list the transformations that are occurring there first. So what transformations do we have occurring in the first one? Y equals 2 cotangent of 2x. Okay, good. So, yep, vertical stretch by a factor of 2. The vertical stretch is occurring from the 2 that's out front. And then there's a horizontal shrink by a factor of 1/2. And that's occurring from that 2 that's inside the parentheses. Technically, you can put parentheses around that 2x in there. All right, so then let's find the vertical asymptotes. So this time we're looking at cotangent. Cotangent, notice, is just multiples of pi. All right, so where are the vertical asymptotes occurring? I don't think it's going to be pi over 4 because we're just starting with pi originally. So if I look at the cotangent line right here, it's just pi. It's not pi over 2. So originally it's multiples of pi. But now we want to multiply by the horizontal factor. And the horizontal factor is 1/2. So that's going to turn into multiples of pi over 2. Now keep in mind that the vertical stretch does not come into play with your asymptotes. Questions with how we got that pi over 2? The multiples of pi over 2 for the vertical asymptotes. All right, one more then to finish us out today and wrap up. We have cosecant of x over 2. So there's only one transformation occurring here. What's the transformation? Good. You guys have gotten really good with your horizontal stretch and shrink factors. That is a stretch by a factor of 2. All right, that does affect the asymptotes. So I'm going to find cosecant in my chart. Cosecant is multiples of pi traditionally. So traditionally, you have multiples of pi. However, how is the horizontal factor going to change our asymptotes now? Yes, you are multiply by that factor, which is 2. 2 times pi is just 2 pi. So you will have vertical asymptotes at multiples of 2 pi. Very good. And again, okay, good. So if it was a 5x over 2, so hypothetically, Zayas is throwing an equation out at us. All right, so if this was a 5x over 2, what would be our horizontal factor then? So if it was a 5x over 2, the factor then becomes a 2/5. So now you are shrinking, right? Because 2/5 is less than 1. So it becomes a horizontal shrink by a factor of 2/5. And then your asymptotes are affected at 2/5 pi, right? So 2 pi over 5, or multiples of 2 pi over 5 is where your vertical asymptotes would occur. So essentially you're just taking whatever that factor was and you're going to multiply that by pi to find your vertical asymptotes for cosecant function. Yeah, it's not too bad. So I really like this chart. I like it for the asymptote piece right here. Basically, these three things: the function, the period, and the asymptotes. I mean, the domain and range and the zeros are useful, but we really like those three things that are boxed there. That's really going to help us. And remember, if it has a plus n pi for the asymptote piece, that is just meaning odd multiples of pi over 2 or whatever that would be after you apply the horizontal stretch or shrink that's occurring. Okay, any questions with these other 4 trig functions today? I know sine and cosine had their full hour with them, and then the other 4 get an hour between them, so it's not really fair. But they're all very similar in an aspect there. All right, that's all I got for you for 4.05. If you have any questions, make sure you send me an email, let me know, or bring them to class with you on Thursday. All right, that's all I got. So have a great rest of your Tuesday, and I'll see you all Thursday morning again. Bye, everyone.